As promised, in our last class, we're going to look at some of the organic chemistry of life. As you know from biology, nearly all organisms get energy from glycolysis, which is the transformation of glucose in the presence of oxygen, it's an aerobic process, into pyruvate. You guys can see that glucose has 6 carbons, generates 2 pyruvates, each of which have 3 carbons, and that energy currency that we're talking about here is ATP. Now, in yeast, pyruvate is further converted under anaerobic conditions in the absence of oxygen to ethanol and carbon dioxide. Okay, and this is called fermentation. For thousands and thousands of years, humans have been making use of fermentation in the production of food. This can be done with yeast, yielding ethanol as the product. It can also be done with bacteria, and in bacteria, these alcohols are converted to acids. So, for example, ethanol could be converted to acetic acid. All of these processes are catalyzed by enzymes in those microorganisms. So, examples of fermented foods with which you might be familiar, sauerkraut, or kimchi, which is simply just cabbage left to ferment. It is nothing but cabbage and salt, and the salt just keeps undesired microorganisms from growing. Sugars in the cabbage are converted by lactobacillus into lactic acid, so it tastes sour. Same with kombucha, which is fermented tea. Sucrose in the tea is converted by yeast and bacteria, ultimately into acetic acid via ethanol. Other examples with which you might be more familiar, this is a sourdough starter. So it contains yeast, which convert the carbohydrates in flour into CO2 and ethanol. So yeast, ethanol. When you have bacteria involved, you get acids. And then finally, this is beer. And to make beer, you simply get sugars, which are converted by yeast into CO2 and ethanol. So how do yeast accomplish this transformation? Well, let's take a look. You can see that pyruvate, which is made up of 3 carbons, is transformed into a 2-carbon and a 1-carbon piece. You would be correct in assuming that these atoms generate ethanol, and the remaining carbon generates CO2. It does look like this carbon-carbon bond is broken. So we're going to need to remove CO2. What is that called again? Yes, that's called a decarboxylation. And then you can see that for the piece that becomes ethanol, it has clearly been reduced. This carbon initially has 2 bonds to oxygen in pyruvate, and it only has 1 bond to oxygen in ethanol. So it will need to be reduced. Now, why does yeast do this? Why does it undergo fermentation to make these products? What use does it have for them? Well, it has no use for them. These are just waste products. Okay, so these are just waste products of fermentation. What use do we have for them? Well, the CO2, it makes our bread nice and fluffy, and the ethanol, some people enjoy drinking. So humans have been using these fermentation processes for years to generate foods. So in addition to these, also yogurt, which is fermented milk by lactobacillus. Okay, so what are these 2 processes that we're going to need to accomplish? Decarboxylation, we've all seen that before. And then also reduction. And so we also have seen reductions before. But how does this happen in biochemical systems catalyzed by enzymes? Well, the decarboxylation of pyruvate requires what's called thymine as a cofactor, and it's in this case in the form of what's called the TPP ylid. You have probably heard about thymine before. It is required for proper functioning of your cells. It's a pretty common cofactor. So what needs to happen for thymine to assist in the decarboxylation of pyruvate is that this hydrogen must be deprotonated. And that happens in the presence of some base, and we're not worrying about exactly what that base is. Deprotonation of that carbon generates what's called the TPP ylid. So ylid And we have the adjacent positive and negative charges that you can see there. And that's part of the reason these charges being adjacent of why this proton is acidic in the first place. Now, this carbon is going to be nucleophilic. It has electron rich. It has that lone pair. And then you can see that this is an electron poor region. And relieving the charge on that nitrogen is probably going to be important. You've seen ylids before. Do you want to make an analogy to the phosphonium ylid that you encountered when you learned the Wittig reagent, or the Wittig reaction, excuse me. So this was nucleophilic a carbon, and you saw that it added to aldehydes and ketones. Okay? All right. So now that we understand where this ylid comes from and how ylids behave, we can look at how we are even able to accomplish this, what's called an alpha decarboxylation. This carboxylate is alpha to this carbonyl. Now, in the past, we've seen beta decarboxylations, okay? So we've seen where the carboxylic acid is actually at the beta carbon relative to another carbonyl. And we had the carbonyl accepting the proton, those electrons coming down and making a double bond in CO2, and then those electrons essentially forming the enol. So there was somewhere for the electrons to go. We generated an enol and a liberated CO2. So that's the beta decarboxylation. Here, what we're essentially proposing is that we're somehow going to have these electrons come down, make that double bond that's in CO2. These electrons are going to go, say, here. All right. Well, what do we have here? We have what looks like the conjugate base of an aldehyde. Are aldehydes acidic at that aldehyde hydrogen? Absolutely not. So this is very unstable. It's a really unstable base. This is not acidic. Okay. So the alpha decarboxylation just seems preposterous. So how does thymine or the TPP ylid here promote or facilitate this reaction? Well, let's start with what we know. So what we know is this, that the ylid will add to the carbonyl carbon. So let's go ahead and do that. Have the lone pair of the ylid add to the carbonyl carbon. That is going to generate for us on this species. Now, one thing, I'm about to make an alkoxide here. And alkoxides do not exist to an appreciable extent in the body. So remember that this reaction is happening facilitated by an enzyme, by a large complex of enzymes. And that enzyme is holding these molecules in it, mostly by hydrogen bonding and then also by the shape of the enzyme. So there's an enzyme here that actually donates a proton to these electrons. So how do I know that I should take a proton from an enzyme? So that's an enzyme side chain. Well, I would do that if I'm going to make an alkoxide in my mechanism. So I'm about to propose this alkoxide. I know that can't be. So oops, need to use the enzyme to protonate. So you're primarily going to be using enzymes for protonation states here. All right, now we actually have a beta dicarbonyl compound. So we looked at this one. This was a beta dicarbonyl compound. We've seen decarboxylations of them in the past. What we now have is also a beta dicarbonyl compound. Do you see it? Maybe not, because it involves an iminium, which is very similar to a carbonyl. But this now does give us this beta relationship between a polar pi bond and then the CO2 that we're going to be losing. So what happens now is that following this first nucleophilic elimination step, which makes perfect sense to us, we're going to have the decarboxylation. So come down, make your pi bond here, and now these electrons are going to keep moving. They're going to scoot over, and you're going to push these over onto nitrogen. Now, how can you rationalize that? Well, you can rationalize that because you have relieving the positive charge on nitrogen. This is a large cofactor. So these R groups, they're just representing the rest of the cofactor. We're just looking at the important part for the chemistry here. All right, now we're trying to get acid aldehyde. Look at our product. How do we get acid aldehyde? Well, it's these two carbons. So clearly we're going to need to break this bond. We also need to install this proton. So we need to somehow make a bond with hydrogen here. Now, if I'm looking at the functional groups, I can see that I do have an enol. And I can protonate the enol. But if I protonate the enol, I'm going to be making the bond to this carbon. And that's not my goal, right? My goal is to be making the bond to the carbonyl carbon. So that looks like a dead end. But I have that enol. I also have an enamine. So I have the nitrogen version of an enol. And it turns out that this is what's going to react. So we have the lone pair of nitrogen coming down, reforming a CN double bond. And then now we'll protonate the carbon that becomes the aldehyde carbon. So where does the proton come from? Remember, it comes from the enzyme. The enzyme does all the proton transfers. It's using all those side chains that you had to memorize in biology. And it uses water as well as proton sources. You can worry about that in bio. So now we have all of the atoms in acid aldehyde intact, and then you can also see that you've regenerated an intermediate that looks a lot like what initially added to the carbonyl, right? So if you're looking right here, this looks a lot like that. In fact, they're the same. So this is a good leaving group. This is a good leaving group, and we're going to, in fact, see that leave. So now we're going to use the enzyme again. The enzyme now is going to use a basic side chain or to deprotonate. That is going to form the carbonyl. So it's kind of like a lone pair push using an enzyme. That's going to break the bond that we already knew had to break, and you're expelling TPP ylide. So you're getting acid aldehyde, and you're expelling TPP ylide, which can go and decarboxylate another pyruvate now. All right, so you want to convince yourself of that. You might need to pause. You might need to rewatch. Understand that this is a tetrahedral intermediate, and it's behaving just exactly like tetrahedral intermediates have behaved in the past. We're having a nucleophilic elimination here. And it's the opposite of the nucleophilic addition that originally happened. Okay. And the proton transfers, instead of being mediated by the solvent, are mediated by the enzyme. So this is really amazing. TPP ylide turns what is a crazy proposal for an alpha decarboxylation into what's actually a nice, easy, normal beta decarboxylation. Now, if you remember, we said there were two things that needed to happen in order to convert pyruvate into ethanol and carbon dioxide. We said they need to have decarboxylation and reduction, right? So we've had the decarboxylation, but at this point, we haven't had the reduction. So right now, we actually have acid aldehyde. We have the two carbons, but we need to convert it into ethanol. And that it will occur by a reductive process. Now consider how you would facilitate this reduction in the organic chemistry lab. You might use sodium borohydride or lithium aluminum hydride. Those are not present in your body. So what your body has is a molecule I'm certain you've heard by name before, so NADH. And NADH is nature's reductant. So let's take a look at how this works. So just familiarize yourself with the reactants and the products here. You can see that this hydrogen is lost. It's no longer here. You can see ethanol certainly has been reduced. And it is, in fact, this hydrogen that's going to go over to ethanol. Now, what do you notice about what NADH has become? It's become NAD+. How would you describe this ring? Yes, it's aromatic. It's an aromatic ring. So that's really the driving force for this reaction, that you generate NAD+, which is aromatic. Okay, so let's look at it. This one is probably going to feel a little bit more comfortable than the decarboxylation. So what we have happening is this hydrogen from NADH is going to add to the carbonyl of acetaldehyde, and those electrons are going to accept a proton from the enzyme. Now this is to avoid generating an alkoxide, right? If I did not get a proton from the enzyme, I would make an alkoxide, and I've told you we're not going to do that in the body. So use the enzyme as a proton source. All right, well, that's how we generate ethanol, but it's not the full story. So look at NADH. The curved arrows I draw definitely don't make NAD+ here. So actually, we have a lone pair push, moving these electrons over, and let me fix those arrows. So lone pair push, move those electrons over, push these over, and that pushes that hydrogen over. And now we get curved arrows that generate the observed product. So how might you accomplish the transformation of acetaldehyde into ethanol in the lab? Using NADH would probably not be all that useful. We'd also have to use an enzyme. Right, so we can reduce aldehydes with sodium borohydride. In the presence of an alcohol solvent, where the borohydride is adding the new hydrogen, the nucleophilic hydrogen, to ethanol. And the proton source is providing the OH. You can do this in a two-step process with lithium aluminum hydride followed by an aqueous workup. Okay, where lithium aluminum hydride is going to be donating the nucleophilic hydrogen, and the workup gives you the OH. Now, if you enjoy any of these fermented beverages, in your liver, the reverse process does take place. So ethanol is oxidized acetaldehyde, catalyzed by an enzyme called liver alcohol dehydrogenase, or LADH. This enzyme requires the cofactor NAD+, which we just drew on the previous slide, and I'll draw it for you again. So why is that? Why does this cofactor require NAD+? Let's think about how this transformation might occur. So you should go ahead and pause and see if you can draw how this transformation might occur. All right, you can see that you're going to be losing this hydrogen and the OH. This hydrogen you lose with its electrons. So in fact, it does add to NADH in this NAD+, in this fashion. So pushing these electrons over and onto nitrogen. While that happens, at the same time, you have the enzyme. It's holding ethanol in place with one of its basic side chains, and it is going to accept that proton, and the electrons in the OH bond come down and make a double bond. So that generates acetaldehyde, and it also generates NADH, which can go off and reduce something. So you use cofactor for one thing, and then now it can go off and do the opposite in some other process. Now, ultimately, acetaldehyde is not the final product of ethanol metabolism in your body. So your liver continues to oxidize acetaldehyde, and it oxidizes it to acetic acid. Now this is water soluble and can be eliminated by your kidneys, which is a nice word for peed out. So how might we in lab accomplish the oxidation of ethanol to acetaldehyde? What might we do? Well, we could use pyridinium chlorochromate in the presence of some sort of dry organic solvent like methylene chloride. Yeah. We could use sodium dichromate, but only if we want to take the primary alcohol all the way to the acid. So that would take us all the way to acetic acid. And then you could also use potassium permanganate to facilitate the transformation to the acid. Okay, now that I've shown you how NAD plus and NADH work, I would like for you to try to draw a complete curved arrow mechanism for this transformation, which is part of the citric acid cycle. I suggest that you start by figuring out what bonds are made and broken. So give it a shot and then come back to the video. I can certainly see that this alcohol is oxidized. So we have the alcohol in the starting material, and then in the product we have a ketone. So there's going to be an oxidation of that carbon, the removal of hydride. I can also see that this bond is broken, so there's going to be a decarboxylation. So I'm going to have an oxidation and a decarboxylation. I might not know what order these steps take place in, but you'll notice I'm just given NAD+. There's also going to be an enzyme because it says biochemical transformation, but it doesn't say anything about TPP-ILID or anything like that. So I'm not going to try to use TPP-ILID for the decarboxylation. I'm just going to use NAD+ for what I know it does. And what I know it does is oxidize. So same way we did before, the enzyme is going to deprotonate. That's going to form the carbonyl, and then the hydride is going to get donated to NAD+. That moves all these electrons around and generates NADH. Okay, so we're going to get from here NADH, which I guess I'll go ahead and draw out. But I'm going to flip it over because I ran out of room. Sorry. Okay, so we have NADH. And then we have this intermediate. And then once you've drawn this, hopefully what sticks out to you, other than the 3 carboxylates, is that you have the magical beta dicarbonyl compounds. You have a beta carboxylase. This is just straightforward. This is just poof, I believe we call it in class. So we can just reform the strong CO double bond. These electrons are going to be forming an enol here, an enolate unless I don't protonate oxygen. So go ahead and take a proton from the enzyme, and that gets you to this enol. So we have an enol, we need the ketone. The enzyme is going to facilitate an enol keto tautomerization. It's going to accept that proton and reform the carbonyl and protonate at the alpha carbon to that ketone. So we're going to protonate right there. There we go. So we have the oxidation, the decarboxylation, was just run-of-the-mill, normal beta decarboxylation, followed by an enzyme-mediated enol keto tautomerization. Really bringing together many of the different reactions that we've looked at this term. All right, is this all about beer and bread? Is this just because I like both of those? No. So pyruvate is definitely good for something else. So pyruvate is the source of acetyl-CoA, so this molecule, which you have certainly heard about before if you've taken biology. It is a crucial building block for a number of biomolecules. It's an extremely important molecule. So not only can pyruvate be converted into ethanol and CO2 so we can enjoy bread and beer, it is also turned into acetyl-CoA so that our bodies can make really important biomolecules such as cholesterol. So let's see if we can propose a curved arrow mechanism for this transformation. Well, we can see that we are undergoing a decarboxylation of pyruvate, and these two carbons are these two carbons of acetyl-CoA, so that we can see for sure. In the lipoamide, we have what's called a disulfide bond, and it is being reduced to the dithiol. So we have a reduction of the disulfide bond to the dithiol, and then we have an oxidation occurring here. Right, we have 2 bonds between carbon and oxygen versus 3 bonds between carbon and heteroatoms in acetyl-CoA. So reduction of the disulfide bond and oxidation of this carbon in pyruvate. So let's see if we can figure out what's going on. We say we'll have a decarboxylation. We know how to do that. We have TPP-ylid. So recall that the first step of this transformation is the ylid adding to the pyruvate. The electrons then accept a proton from the enzyme. The alternative is generation of an alkoxide, and that is not going to happen. How do you know when to use the enzyme as a proton source? Well, if you generate an alkoxide, then oops, you needed to use it as a proton source. So just go and revise what you drew. All right, so now from here, we have this beta dicarbonyl, or really it's a beta aminium carbonyl, but regardless, we have our beta decarboxylation that's occurring. So the electrons come down, make the double bond of carbon dioxide. These electrons slide over, and the nitrogen accepts them. So that generates the CO2 waste product. And this enol enamine system that we discussed before okay, so here's the enamine this time. So we're going to go ahead and use that to do the next step. So what happens next might not be obvious. This time we're not going to protonate. And why not? Well, last time we protonated because we were making acetaldehyde, right? And so from here we protonated that carbon to get this proton. But that's not what's happening here. We're not getting acetaldehyde, we're getting acetyl-CoA. So it's a little bit different now what happens. Just like last time we saw this intermediate, we are going to have the enamine, that nitrogen, donate its electrons, and something is going to happen at this formerly carbonyl carbon of pyruvate. But this time what happens is it attacks a lipoamide. So it's going to attack sulfur of lipoamide and break the sulfur-sulfur bond. That generates this intermediate. So we've made a bond with that, so that formerly carbonyl carbon. And let me show, I'm going to make a point here. All right, so I'm about to draw an S minus, so a thiolate, and that is going to trigger to me, oops, I just forgot to do an enzyme-mediated proton transfer, so we're going to fix that. So right here, let me show you, instead of having those electrons go to sulfur, they're going to pick up a proton from the enzyme. Really illustrates the role of the enzyme. Okay, so here we go. And now what we've made is a tetrahedral intermediate. I know it's super hard to see in the complicated context here, but this is a tetrahedral intermediate, and you know what they can do. They can collapse to reform carbonyls. So just like it happened before in the acid aldehyde synthesis, we're going to have the enzyme come and accept that proton. The electrons from the OH bond reform the strong CO double bond. And, sorry, that was the typo. All right. And so we need to break one of the remaining bonds to the carbonyl carbon, and we're actually going to expel the TPP ylid. So we're going to expel the TPP ylid. We're going to get this interesting intermediate. All right. So this is called a, well, you tell me actually. So what do you think this functional group is? Yeah, it's a thioester. So is acetyl-CoA. Acetyl-CoA is a thioester, but it just has a different thiol. So that that's coming from here. So now this is going to act as a nucleophile. Let's show that. All right, so we're going to have an you're going to love this. So we're going to have an enzyme come and deprotonate. Those electrons are going to come, make a bond to the carbonyl carbon, so just the nucleophilic addition. It's just weird because I'm showing that the SH electrons do that. That is going to, it looks like it makes an alkoxide, right? An O minus. No, we know that doesn't happen. So what's really going to happen is oxygen is going to get a proton from another enzyme. That's going to generate, again, a tetrahedral intermediate, and I promise we are almost there. And the second tetrahedral intermediate is going to collapse to expel the thiol that came from the lipoamide. But again, you're not going to expel an S minus thiolate, so just grab a proton from the enzyme. And then that generates the thioester and the dihydrolipoamide. But it simply is, simply, right? I know it's very complicated, but it simply is a nucleophilic addition or a lone pair push, a collapse of the tetrahedral intermediate to expel a good leaving group and form a strong CO double bond. So why in the world are we talking about this? Well, for a couple of reasons. Let's quickly think about thioesters. So where do you think thioesters rank among carboxylic acid derivatives? So where would I put them in terms of reactivity? Well, it might be good to think about how they compare to esters, right? So it turns out that a thioester is more reactive than an ester. There's a couple ways that you can rationalize this. One of those ways is by thinking about leaving group ability. Okay, so let's compare the thiolate versus the alkoxide. The thiolate is the conjugate base of a thiol. Thiol has a pKa of 12. An alkoxide is the conjugate base of an alcohol, which has the pKa of 16. So more stable conjugate base better leaving group. So that's one way to rationalize why the thioester is more reactive than the ester. And there's also some orbital interaction issues going on here. So if you think about an ester and a thioester, these resonance structures are going to contribute to their character. Okay, where you have either oxygen or sulfur overlapping with the carbon of the carbonyl. And for an ester, this is a much more significant resonance structure. So the oxygen of the ester is donating to the carbonyl much more than for the thioester. Sulfur's in the third row, and it has pore overlap with carbon. The orbitals are not the same size. And so that resonance structure is not very contributing. And that ends up making the thioester more reactive than the ester. So did that answer the question of why thioesters like acetyl-CoA are so useful in biological systems? Yes, it should. The thioester is nature's acid chloride. Okay, so it's the equivalent of an acid chloride for nature. Obviously, acid chlorides are super reactive. You can't have them in your body, but you can have the thioester, and it's the equivalent of nature's acid chloride. You can turn it into ketones. It's like you could turn an acid chloride into a ketone. You can turn a thioester into a ketone. This is really important in fatty acid synthesis. It can be turned into an aldehyde, etc. So the thioester is nature's acid chloride. It can also, you also see it behaves like an ester. It can do Claisens. We've learned a lot, so let's recap what we learned. We learned that yeast can convert pyruvate to ethanol and carbon dioxide. And we knew there were two main processes that were occurring here: decarboxylation and reduction. Nature does these differently than we do, and the decarboxylation is going to occur with a cofactor called thiamine diphosphate, TPP, and it's going to facilitate the decarboxylation as an ylid, so the TPP ylid. What does it do? Well, it turns what would be a crazy alpha decarboxylation into a beta decarboxylation. So you should be able to do a TPP-mediated decarboxylation. We learned that the body and microorganisms can conduct reduction reactions using NADH. These are enzyme-mediated processes. I did not write enzyme here, but it is an enzyme-mediated process. The body can also conduct oxidations. So oxidations using NAD plus as the oxidant. Okay. We brought it together a little bit here. We saw that we were having an oxidation and a decarboxylation happen. Once we did the oxidation, we got an intermediate that can undergo decarboxylation on its own without TPP ylid. And then finally, we looked at the formation of acetyl-CoA, a super important building block in your body. And this reaction, the transformation, used the TPP ylid to do the decarboxylation. So that was the first step. And then as far as new chemistry, we looked at acyl transfer. So that was really the new chemistry here. We did an acyl transfer. Now, we can bring all of this together and revisit what we discussed on the very first day of Chem 12B this semester, which was the amazing transformation of 18 acetyl-CoAs that you now know how the body makes from pyruvate, from glycolysis, into cholesterol. I'm going to give you a break to process what you just learned and tackle this in another video.